Dear learners, greetings from IIT Guwahati. We are in the MOOCs course Computational Gas Dynamics, that is week 1, compressible flow and isentropic relations. Now, in today's lectures, we will mostly focus on isentropic flow. Under this segment, we will try to emphasize the compressible flow, which we have concluded in our previous lecture. Then another important parameter that pops in is the compressibility. Then pertaining to the isentropic flow, we are going to discuss some of the important thermodynamic aspects relating the fluid mechanics concept to the thermodynamic properties. So, there we will define static parameters and stagnation parameters in a compressible flow domain. In our last segment, we talked about the flow regime. The flow regime is classified in terms of its Mach number, but the theoretical background that how those Mach numbers pops in will come with some graphical representation of compressible flow analysis, and we will call this as an adiabatic ellipse. Then finally, whatever relations you develop for the compressible flow system, and if you are going to represent them in terms of data, then we are going to introduce a table called as isentropic property table for compressible flow. So, these are these major segments for this lecture. So, we will start with the part 1 of the lecture, which will mainly involve compressible flow, compressibility and stagnation flow properties, static and stagnation flow properties. So, in our previous segments of lectures, we have completely emphasized about the incompressible flow and compressible flow domain. So, there it was quantified that compressible flow domain comes into picture when there is a density variation of more than 5% and above. And under some circumstances in terms of Mach number, the flow behaves as incompressible flow, and for certain Mach number above a limiting value, the flow behaves in a compressible flow domain. So, what is that Mach number we are going to find out. Now, these are some of the important points that we have highlighted in our previous lectures, like liquids are incompressible, gases are have the dual nature. So, for if you look at actually the incompressible flow equation, it is described through volume flow rate, whereas compressible flows are defined through its mass flow rate, because density becomes a significant factor here. Other important aspects what we have said is that the variable density flows are routinely called as compressible flow. So, there the governing equations, continuity, momentum and energy equation need to be solved simultaneously, which means that in an incompressible flow domain, mass and momentum equation, if we solve that, then we need not have to couple energy equations, and energy equations can be solved independently. But in a compressible flow domain, all three equations has to be solved simultaneously along with the equation of states, and it is mainly applicable for gases. So, just to emphasize the fact what a compressible flow domain can be, we can say that air is about 20,000 times more compressible than water. So, water is incompressible, but we can compress the air 20,000 times more as compared to water. So, this is how you can imagine that how much pressure is going to build up in a compressible flow domain. What we have not touched in our previous class is the parameter that actually virtually defines the flow changes due to the density. Now, in our previous segments, we emphasized that density variation occurs in a flow domain, but the question remains why that density varies. Normally, density varies, density for incompressible flow, pressure and densities are related. For a compressible flow domain, the density can vary due to pressure as well as temperatures. So, this is where the catch lies, that pressure and temperature both can change to make necessary changes for the density. So, for in a quantitative measure of compressibility is nothing but the volume of elasticity, and that is true for liquids, and for ideal gases we can bring out the equation of state in terms of density modulus of pressure. So, if you look at the basic definition, changes in the static pressure for a fluid, we can define that delta P is equal to minus E divided into delta V by Vi. Vi stands as the initial volume. So, a given system at its initial volume and pressure, when it is compressed, then the change in the static pressure can be defined in this manner through a factor called as volume modulus of elasticity. And now, the same expression, if you can write it for an ideal gas, we can represent in terms of P is equal to rho R T, and keeping this temperature T constant, that is in making it as an isothermal process, one can bring down these particular expressions, what happens with a change in the pressure delta P with corresponding change in the volume delta Vi, then we can bring back the basic expression of delta P in this form. So, here delta P now it becomes Pi into delta V by Vi. So, here if you compare these two equations, then we can find out what this volume elasticity is nothing but its initial pressure. Then another expression one can find out, that is mass flow rate per unit area. So, again that remains conserved. So, density into velocity, which is the initial mass flow rate, becomes final mass flow rate density, that is rho I plus d rho is equal to into Vi plus delta V. Here V stands as velocity. So, if you can simplify this particular expression and neglecting higher order terms, what relation we get? Relation between density and velocity. So, here we get a relation between the change in the density with respect to velocity, and here we get the change in the pressure with respect to change in the volume. So, from these two equations one can bring down the changes in the pressure delta P as E times d rho by d I, delta rho by delta I. So, what it says is that change in the pressure is associated with change in the density. So, this is the catch that lies here, and based on which we can define a factor what is called as a compressibility of the fluid. So, compressibility of the fluid compressibility is defined as the fractional change in the volume of fluid element per unit change in the pressure. So, if the change is achieved at constant temperature, then it is called isothermal compressibility. If it is done through isentropic manner, it is called as isentropic compressibility. So, thereby we give a thermodynamic meaning for this, how that how that change in the pressure to change in the volume is associated. So, if you say that basic definition for the compressibility of the fluid, which is tau, that is defined as 1 by minus 1 by V stands as specific volume into delta into dV by dP. So, here it is a differential equations, but we can make it more meaningful by assigning a thermodynamic process to it. That means, instead of defining the compressibility, we call this as isothermal compressibility. That means, this change is achieved by keeping temperature constant. Similarly, this change can be achieved by keeping entropy remains constant. So, that way that is the way we define this isentropic compressibility tau s, which is 1 by rho dou p by dou r at constant s. So, if you recall our previous lecture and this term, this tau s is related to speed of sound, but here the basic, but that number basically comes from the basic definition of compressibility. So, this is how we deal with gases. Now, coming back to liquids, there is no effect of temperatures. So, we can write that as for relations, pressure and density relation takes in some empirical form, P by P A is equal to B plus 1 into rho by rho A to the power n. So, here so this is this relation is not relevant for our analysis, but however, if I recall our previous concept by introducing the speed of sound and with this isentropic compressibility factor, one can find out that the fact that if you calculate the speed of sound in air, this is close to 341 meter per second, by considering the fact that it is gamma square root of gamma r t speed of sound. Whereas, here if you speed of sound in the water, we can use it is square root of gamma p by rho, because p by rho is not exactly equal to r t, and if it is true, that is only true for the assumption of ideal gas. So, what we say here, while calculating this A, we can have two expression. One is square root of gamma p by rho and other expression is square root of gamma r t. So, this we calculate as 1500 meter per second, taking the medium as water, and this is 341 meter per second, that is for air. Now, to give a realistic number, one can say that if we want to define isothermal compressibility for water and air, we can find that for air this value is much larger than that of water. So, this is essentially true, that is the reason liquids are incompressible. Now, coming back to this compressible flow domain. So, in our last segments, we say that Mach number, we introduce the flow regime. When you say this Mach number less than 0.8, which is called as subsonic flow. But much before that, the effect of compressibility might have induced. So, that is the reason we want to try to find out what is the limiting value of Mach number from which the effect of compressibility comes into picture. So, that is essentially the main theme of this particular slide. So, for that reason, what we are going to look into is that we can revisit this Bernoulli's equations, P plus half rho B square is equal to constant, assuming the flow to be incompressible, and this P constant can be assumed to be a fixed value, that is we call this as a stagnant pressure, stagnation pressure. So, we can now find out the difference between the stagnation pressure and static pressure as half rho V square. So, here so if you have this from our previous analysis, we have found out that delta P by E is equal to delta rho by rho I. So, from this expression, we can find out this delta P in terms of E and density change. So, from this we say delta rho by rho I is equal to Q I by E. Here you Q I you introduce as half rho I V I square, and here we call this as a dynamic pressure. So, compressibility effect is neglected when delta rho by rho is much less than 1, or delta Qi by Q is much less than 1. And this is how we talk in terms of density change. But again we have to see this density change, how it is related with respect to Mach number. So, again we revisit the expression speed of sound as a square, and that we can find this expression speed of sound in terms of E and rho I, and the density change can now be related rho I by E I in terms of Mach number. So, these are the different steps that how rho I by delta rho by rho I becomes half m square. So, in this is a very basic relations between the density change with respect to Mach number. So, if this Mach number m square by 2 is much less than 1, which means m much less than 0.3, then density change would be 5% or less. So, which means for the density change to happen less than 5%, the Mach number that means flow is treated to be incompressible. Under that condition, Mach number is much less than 0.3. So, what it means that limiting case for Mach number is 0.3, which implies effect of compressibility into flow field. In the flow field. So, that is the catch what we say. So, many times it is almost difficult to measure the density, rather Mach number is the catch that which will give you whether the effect of compressibility has to be taken into account or not. But however, any flow that ranges from, now we can reframe our subsonic flow definition, any flow which is higher than 0.3, which has Mach number higher than 0.3 and lesser than lesser than 0.8 is categorized as subsonic flow. So, this is the theme of this analysis where compressibility effect is taken into account. Then moving further, talking in terms of compressibility, now we are going to introduce the isentropic flow, and as I know that when there is a change, if you look at this particular figure, any given flow field can be described in terms of streamlines. The tangent at any point in the stream gives the direction of the velocity. Now, during the motion of fluid element along a streamline, its property value changes, its velocity changes, its Mach number changes. Now, in an isentropic flow field, what we say is that entropy remains constant in this flow field. Now, any point on this flow field, that is at point A, the properties values can be assigned as some number, velocity, pressure, temperature, density, internal energy. Now, when this element changes its state to B, that means it goes to another state, the property values can be again is going to change. Now, this change the property value is going to change, but it is happened through isentropic manner. But what we call this as a stagnation properties, that it is a specific case in which we assume that the fluid element is hypothetically slowed down in an isentropic manner to 0 velocity. That means, at whatever velocity it is having at point A, if you bring down to its the velocity of the fluid to a 0 value, that means we stagnate the fluid, then ultimately the property values with respect to that point will be treated as a stagnation or total properties. In other words, when you stagnate the fluid, we converted the kinetic energy of the fluid element to the pressure energy. So, entire fluid is now becomes stagnant and it has higher pressure energy. So, such a concept we call this as a stagnation value. So, this is true for any property of the fluid. So, you can call this as a stagnation pressure, stagnation temperature, stagnation density likewise. Now, to bring the relation between stagnation pressure and static pressures, we want to revisit our earlier expressions where you define the state 1, the fluid, when the fluid passes in a rectangular control volume with a constant area cross section, then the property value changes from 1 to 2. But what we are going to look at here, and when you say it is at 1, these properties are defined as static properties. When it is at state 2, it is also defined as a static properties. But what we are trying to say that if when the change of states happens from 1 to 2 in a hypothetical manner, so that at point 2 your u becomes 0. So, correspondingly when we stagnate the fluid, the other properties will be assigned with a number which is called as a stagnation value, that is defined as P naught, T naught, rho naught. What it means? The corresponding any arbitrary state initial value of pressure, temperature and density, the corresponding stagnation value becomes P naught, T naught and rho naught. So, to do that we want to find out we want to use the energy equations that is for an isentropic flow H plus U 1 square by 2 is equal to H 2 plus U 2 square by 2. Now, from there if this state 2 becomes stagnation property, so you can find out the relation between static temperature to static temperature to stagnation to static temperature, then this can be represented in terms of Mach number. So, correspondingly once we know static temperature to stagnation to static temperature ratio, we can compute static pressure to static pressure, stagnation pressure to static pressure ratio, stagnation density to static density ratio in terms of Mach number. In another situation, we are going to calculate that condition static versus characteristic state. So, static means if you say that initial conditions are stagnation and final condition is characteristic state, which means at this state you say Mach number is 1 and U becomes A star, U star, all the values becomes star value. So, we revisit the energy equations for the initial state, that is the basic expression. We can write in terms of Mach number, initial state and this state 1 and state 2. Now, here the catch applies that state 1 is arbitrary state and state 2 is the stagnation state, and this is one expression we can find out. Another expression we can find out if this is the stagnation the initial state is arbitrary state and second state is state 2 is characteristic state, that is at m is equal to 1, u 2 is equal to a 2 is equal to a star. So, we get two relations, then both the relations can be equated to find a relation what is between stagnation to characteristic state. So, that becomes the ratio what we call as this particular expression T star by T naught, which is 2 by gamma plus 1, that is the almost extreme case. Initial state is stagnation state, final state is characteristic state, which means gas changes its state from its stagnation value to a state where it has it has Mach number 1. That means, flow is accelerated from 0 velocity to a sonic value. Through this process, what happens with respect to change in the temperature and change in the pressure and change in the density. So, if you look at this expression, this becomes a fixed number for air. So, air gamma is equal to 1.4 and this number turns out to be T star by T naught is equal to 0.833, P star by P naught 0.528, rho star by rho naught is equal to 0.634. And moving further, we can have more emphasis in terms of Mach number. Again we say that characteristics Mach number and arbitrary state Mach number. So, one relations can be obtained, that is from one dimensional equation. If this is your arbitrary state and this is your characteristic state, one can frame a relation between a Mach number and characteristics Mach number. So, characteristics Mach number is nothing but which is m star, which is this is star condition, and here we have m star and a star. So, if you try to correlate this a value here and a star value here, and if you have u here and here also u star. So, both are same here because Mach number m star is equal to 1, it is not m. So, at this state your m is equal to 1. So, then we can find a relation between Mach number and characteristics Mach number. So, one important expression inference that we can draw, that m star acts same fashion as m, but however, when m approaches to infinity, looking at the expression where when m approaches to infinity, m star approaches to a finite value. So, this is how the catch lies that I was trying to emphasize, that when we are dealing with a mathematical equations to solve, for which m star approaches infinity, which is actually cannot be solved in a conventional manner. So, there if you want to express Mach number in term characteristics Mach number, this becomes a important computational tool, because m star becomes a finite number, and here m star is square root of gamma plus 1 by gamma minus 1. So, now we are moving on to the second part of this video for this lecture, and where in continuation of static to stagnation flow properties, we will define some term what is called as maximum speed and characteristic speed. So, maximum speed is gas attains a maximum speed when it is hypothetically expanded to 0 pressure, at which static temperature will be absolute 0, and the maximum speed of the gas represents the speed corresponding to complete transformation of kinetic energy to random associated with the random motion of gas molecules into directed kinetic energy. So, that means this is almost the what is that it is the characteristic speed of the speed of the gas at the sonic state. So, maximum speed is also related to the characteristic speed. Now, to find this expression in a mathematical term, we want to revisit this energy equation, fundamental energy equation, h1 plus u1 square by 2 is equal to h2 plus u2 square by 2. And from these expressions, we define the term stagnation enthalpy, and we get the total temperature as T plus u square by twice Cp. This is one expression. And gas attains to a maximum speed when T tends to 0, u tends to E max, and of course, Cp is nothing but gamma r by gamma minus 1. Now, if you put this expression here, when u becomes u max, then u max is equal to square root of twice gamma minus square root of twice 2 by gamma minus 1 into a0, where a0 is nothing but your stagnation speed of sound, which is related to the stagnation temperatures. So, this is how the characteristic speed, this is how the maximum expression for maximum speed. Now, coming back to the characteristic speed, we already know that u star is equal to a star. So, h star can be related to this, and this u star is nothing but your u max. So, this u star is equal to a star, and A star can be estimated to be this twice gamma r T naught divided by gamma plus 1 square root. So, from this expression we get the ratio of A by A naught, A star by A naught square. So, by putting this number one can correlate the information what happens to these values. For gamma is equal to 1.4. So, basically we have done so much derivations, and ultimately what we are trying to find out what is the value of A star by A naught for AR, for which gamma is equal to 1.4, A star by A naught is equal to 0.92, U max by A naught is equal to 2.24, U max by A star is 2.45. So, essentially these numbers are nothing but the limiting case or most ultimate case that we are going to achieve when in a compressible flow domain. And next objective of our discussion is that how to represent the concept of isentropic flow in a graphical manner. This is one objective. Second objective is that in our previous lecture we defined various flow regimes which is normally encountered when the flow passes over an airfoil. And there we classified the flow regime by putting down some sorts of numbers, Mach number, limiting situation, Mach number 0.8, 1.2, supersonic Mach number, hypersonic Mach number, and so on. So, what is the technical concept behind these assumptions? To do that, we are going to introduce a term that pertains with respect to isentropic flow and what is called as a adiabatic ellipse. The word ellipse is a graphical representation of a curve. Now, why it is called as adiabatic ellipse and how it can be related to compressible flow domain with pertaining to isentropic flow. So, we know from our previous discussion when there is a large relative change of speed between the body and compressible fluid surrounding it, the variation of density and with speed influences the property of the flow field. So, the Mach number which is defined as the directed kinetic energy to the random molecular kinetic energy. So, this is how we can correlate ratio of kinetic energy to the internal energy in terms of Mach number. This we have already derived in our previous lectures, and this is the proof of that how Mach number is related to kinetic energy to internal energy. Now, it is possible to have a graphical representation for the speed of sound as a function of speed of gases in a steady compressible domain. So, what is the basic definition of adiabatic ellipse? So, the adiabatic ellipse is the locus of all points that turns out to be an ellipse, and all points locus of all points turns out to be an ellipse, and all points on the ellipse have same total kinetic energy. So, basically speaking, this directed kinetic energy and random kinetic energy represented in terms of Mach number or velocity to speed of sound in such a way that all points in the ellipse will have same total energy. So, each point on the ellipse differs from other owing to the relative portion of thermal and kinetic energy and corresponds to a different Mach number. So, what is the basics how that equation turns out? That if you say it is an equation ellipse, then how it turns out to be? Then you recall the expression for stagnation enthalpy H naught is equal to H plus U square by 2. So, we write this from this equation we arrive at this particular expression U square plus twice by gamma minus 1 A square is equal to twice by gamma minus 1 into A 0 square. So, from this expression we can reframe this equation in this form. So, here we introduce the term, the expression for u max square is equal to twice gamma or T naught by gamma minus 1, and that is nothing but is equal to twice by gamma minus 1 A 0 square. So, by putting this expression in this equation, what it turns out to be that final equations for this adiabatic ellipse is this. So, it is u square by u max square plus a square by a 0 square is equal to 1. So, if you look at the bottom side in this equation, u and a are that any arbitrary state, u max and a 0 is the upper limit or maximum values of u max is the maximum speed, a 0 is the stagnation speed of sound. So, these are that means the what you say, the directed kinetic energy which is expressed in the u and corresponding maximum value is u max, random molecular kinetic energy which was a, and for its maximum value is a 0 square. So, it becomes 1 and this is nothing but your equation of an ellipse. So, by knowing these expressions, one can draw a curve that is u and a and draw an ellipse. So, that equation of ellipse is represented by here. So, where x axis is u, y axis is represented by a. So, what is u max? So, if you say that major axis is u and its maximum value is u max. So, this point represents the u max and minor axis of this ellipse is a. So, maximum value is a 0, this is the point. So, each point and if you go from u max to a 0 on this curve, you can say there is a change in the slope. That change in the slope is associated by the parameter dA by du. Now, and that dA by du one can correlate in terms of Mach number. So, if you are going along this direction, you can say that Mach number at every point on this flow field changes. So, this is how the representation of the ellipse. Now, let us see that if you draw a line which is 45 degree on this u of axis u and a, then what we can say, this point wherever it crosses at 45 angle, if you draw a line wherever it crosses, this point represents the location where you have say Mach number is equal to 1. So, here the catch remains there that 45 degree line, one side we have dominance of u, and on the upper side of Mach m is equal to 1, there is a dominance of a. So, here if you try to correlate the flow regime what we have defined so far, this falls under this. That means, in this zone we are actually looking at here, and in this zone we are actually looking at here. So, if I give you more precise information and take a quadrant of that segment, take the quadrant of this segment, then what we can represent as 4 major regions or segments 1, 2, 3 and 1, 2, 3, 4 and 5. So, when you are in the zone 1, when you say there is a dominance of, that means when you have zone 1, we are in the incompressible flow regions. that means dominance of A is more, which means informations are propagated when the speed of sound is higher. So, zone 1 is completely incompressible. Now, compressibility effect comes into picture at some point on this ellipse line where you have which had Mach number of 0.3. That and beyond 0.3 we are entering into subsonic zone, that is zone 2, that is subsonic flow, and the subsonic flow continues from 0.3 to 0.8, somewhere between 0.2 and 1. That is 0.8 and 1.2 we are encountering this transionic flow, and the line which is drawn at 45 degree represents the location where you have sonic flow or Mach number 1. Now, if you are moving further, that is entering into beyond this region, when you are entering, so any value which is more than, for which Mach number more than 1, so this is treated as a supersonic flow. Any value that is more than 5, this is treated as a hypersonic flow. So, supersonic flow, any value that is more than 1, transionic case any number between 0.8 to 1.2. So, this is how adiabatic ellipse gives the complete information of the flow field, and which actually we correlated by giving an example for flow past an airfoil, where we classified this flow regime as subsonic, transionic, supersonic and hypersonic. So, correlation between these two with an concept of isentropic flow gives the complete information of flow field in a compressible domain. So, this particular expression of Mach number gives the slope on the any particular point on the ellipse. So, finally, when you come to the summary of this adiabatic ellipse, we can say that change of the slope from point to point indicates the change in the Mach number. Slope gives direct comparison of relative magnitude of thermal and kinetic energy in a steady flow compressible domain. Low Mach number flow changes in the flow parameter are mainly associated with velocity of the gas. At high Mach number flows, changes of property parameter are mainly associated with speed of sound. In the limiting case of Mach number 0.3 or less, the flow is treated as incompressible. The last part of our discussion in this lecture is to introduce the property table for isentropic flow. So, in our previous discussions, basic thermodynamic equation starts with isentropic relations. From these isentropic relations, we defined this particular 3 fundamental isentropic relations between static and stagnation values. For pressure, temperature, density in terms of Mach number. Now, it is very easy to, we can put for different values of Mach number, we can find the property ratios. But there is another way of looking at the things. One can think of, by changing the Mach number, we can find out a different pressure ratios. So, this is represented in terms of table, and it is called as isentropic table. So, isentropic table defines the isentropic relations which are in the function of Mach number. This particular data which is presented here, it is taken from a reference book, John D. Anderson, where, and this is the extract, just to try to see how to use this table, is that you in our given problems, you might be knowing only Mach number, or you might be knowing only static to stagnation pressure ratio, then how to compute the other parameters. For example, if you are if you know the Mach number, then from the table we can calculate. Let us say we are looking at Mach 1. So, Mach 1 number falls here. So, for this Mach number we can find out the stagnation temperature ratio, stagnation pressure ratio, stagnation density ratio, stagnation temperature ratio. Then for example, if you know the density ratio, let us say density ratio at this value 0.8, let us say it is 0.84. So, this density ratio is known. So, once this, if for this number one can actually, if you go along this horizontal line, you can find out its corresponding Mach number is 0.84. So, that is the way one information will give you the complete, one data will give you the complete flow informations. This is how this table is being used. Now, with the concept of today's lectures, let me try to elaborate some of the numerical problems that gives you more conceptual meaning for these lectures. One such problem, and this particular problem mainly deals with the relation between the relating isentropic flow or isentropic relations with respect to Mach number. So, what is happening in the first problem is that combustible gases undergoes isentropic expansion in the rocket nozzle. Initial state is given. So, this initial state we call this as a stagnation state. This is how you have to interpret right now, because this pressure is very high, 15 bar and 25 degree centigrade. Now, as if the gas is in stagnation state with very high pressure and temperature, and it expands at supersonic speed in a nozzle. So, rocket nozzle, and this rocket nozzle is a CD nozzle, convection division nozzle, to a temperature 1350 Kelvin. So, through this process the gas expands, that means it attains certain Mach number. So, we need to calculate what is that Mach number and velocity at the exit. So, data which for to solve the problem we have given molecular weight of these gases and specific heat at constant pressure. So, to solve this problem, so let me draw a particular rocket nozzle. So, for which your initial condition is P naught, that is 15 bar, T naught which is 2500 Kelvin, and we call this as a stagnation. Now, this gas expands while passing through this nozzle. So, ultimately at the end of expansion, the nozzle temperature P becomes 1350 Kelvin, and your it attains some Mach number, and let us say in this case it attains P2, M2 and U2, that is velocity. This is not known, but other data that is known is your molecular weight is 12 for the gas and Cp is 4.157 or 4157. Joule per kg Kelvin. So, by knowing this information, what we don't, because if you recall this thing, we need the value of gamma, and that is nothing but Cp by Cv. So, we do not have information of Cv. So, Cv is equal to Cp minus R. And R we do not know, but because we have given molecular weight. So, R becomes R bar by M. So, R bar is 8314, that is universal gas constant by 12. So, putting this number we can get R as 692.8 joule per kg Kelvin. So, we have Cp R, then Cv can be estimated as 3464 joule per kg Kelvin. So, once you know Cp and Cv, gamma is becomes 1.2. So, this data is required for our analysis. Then we can use these isentropic relations. Here we can write P2 by P naught is equal to T2 by T naught to the power gamma by gamma minus 1 is the first isentropic relation in terms of pressure and temperature. So, from these equations we can calculate P2 as 15 in P naught into T2 is 1350 by 2500 to the power 1.2 divided by 0.2. So, this is 0.372 bar. Now, we recall this isentropic relation, that is P naught 2 by P2 in terms of Mach number, that is 1 plus gamma minus 1 by 2 m2 square to the power gamma by gamma minus 1. So, this equation can be solved for m2, that is equal to twice by gamma minus 1 into P naught 2 by P2 to the power gamma minus 1 by gamma minus 1 whole square root. So, we have all the values P naught 2, P2, then M2 can be calculated as 2.92. And once you know M2, we can also calculate A2, that is speed of sound at state 2 square root of gamma R T2 1.2 R is 692.8, T2 is 1350 square root. So, this number is 1060 meter per second. So, once you have A2, then V2 is equal to M or U2 is equal to M2 A2, that is equal to 3095 meter per second. So, what I am trying to say, a stagnation pressure of 15 bar and 2000 pressure and temperature of 15 bar 2500 Kelvin, when a gas when expands in a nozzle, it can introduce a jet velocity or Mach number into the medium as close to 3. So, this is the catch or nature of equations that isentropic relations can be used to find out the velocity and Mach number in a flow field. The second problem pertains to the fact that how for a given data, how you are going to introduce or how you are going to use this gas table. So, these relations anyway we derived. So, if you give in Mach number or if any this ratio left hand side or right hand side any value, one of the value is given, we can find out the other informations. But here we are trying to solve this particular problem using this gas table. This gas table we have extracted from a book, which you normally while solving the problem you can use this book to refer the data. But I have taken some extract from that book, so that how to use the data from the book I can explain. So, what is the problem defines that at any arbitrary point in a flow field the data is given. So, given data is that at Mach 1.5 pressure value is given 90 kPa, temperature value is given 250 kPa, 250 Kelvin. So, we want to find out stagnation pressure value. These are the static value, we want to find stagnation value. So, we have known the data for 1.5. So, from this table you see where is the data for 1.5. So, referring here this number corresponds to a value 1.5. So, for that 1.5 if we can get other information, that is P naught by P is 3.671, T naught by T is equal to 1.45. So, this will give you P naught as, you know P, so P naught as 330.4 kilopascal. This will give you T naught as 362.5 Kelvin. So, this is the stagnation value of flow property corresponding to this static value. So, this is static and this is stagnation value. Now, another parameter it is asking what is the characteristics case pressure. The second part of the problem is characteristics value. Which means here we have say star value. So, for which your m goes to approaches to 1. So, which means for m is equal to 1, you take this data. This data corresponds to a situation where m is equal to 1. So, this will give you P naught by P star is equal to 1.893, T naught by T star is equal to 1.2. So, we know P naught. So, this can be, we can find out P star is equal to 174.5 kilopascal, T star is equal to 302 Kelvin. Then we can have A, so what you also require the flow velocity. So, we can find out A is equal to square root of gamma RT. So, gamma can be taken as 1.4, R is 287. If no data is given, then you can use the sea level data. Temperature in this case is 250. So, which means A is here is 317 meter per second. So, we have A, we have Mach number, this will give you B is equal to m times A, and that is equal to 475.5 meter per second. So, this particular data corresponds to velocity of the object as 475.5 meter per second. So, with this I conclude this lecture for today. Thank you for your attention.